Okay, so this SI6 problem has basically three calculations in it. Here's our picture. We have, here's our unit circle in the XY plane, oriented counterclockwise as seen from above. And let me draw this in black just to emphasize that that's the curve we're talking about there. And I claim that that can be thought of as the boundary of multiple different surfaces. For one hand, that's the boundary of that disk, right? It's also the upward oriented. It's also the boundary of that hemisphere oriented, what you might call outward. Okay, is that cool? Okay. And it's also the boundary, if you play the little orientation game, it's the boundary of this lower hemisphere oriented inward. It has to be oriented inward in order for yeah, exactly. You've got to like orient your thumb and then, you know, think about the way that it sort of wraps around and stuff. But this is an inward orientation there. So let me give names to these surfaces. I'm going to call this one, let's see here. I'm going to, for H for hemisphere, how about that? So I'll call it H1 for the upper hemisphere and H2 for the lower hemisphere, and then maybe D for the disk. All right, and so just one at a time. Let's do the upper hemisphere first. So the flux of this vector field through the surface H1 is, well, F dot ds through H1. And how do you calculate this? Well, you parameterize H1 and then you play the game. So let's parameterize H1. I'll do the first one and I'll let you guys do the rest of them. Okay. So how do you parameterize H1? Well, H1 is part of the sphere defined by rho equals 1, so I can use the spherical graph parameterization, and I get that x, y, and z are going to be sine phi cosine theta, sine phi sine theta, and cosine phi, where phi and theta range over certain values. And now this is how we really describe the upper hemisphere, is by what values we choose for phi and theta. Now, phi represents angle off of the z-axis, and clearly that starts at 0, and I'm still in the upper hemisphere all the way down to where I get to phi equals pi over 2. And that's where I need to stop, because I don't want to go down into the lower hemisphere. So phi is going to go from 0 to pi over 2, and then theta goes all the way around, of course, so this is 0 to 2 pi. And I claim if you take this parameterization and plug it into there, in other words, compute x phi, compute x theta, compute n, which of course is the cross product of those, plug in chapter 5 computation, and you'll get a value.
You said n was the cross product?
Yeah, n is the cross product of the two partials of the parameterization. Oh, sorry. Sorry, I had that off camera. Yeah. Does that make sense? Chapter 5 techniques? Let me write it down. Okay, so what's x phi? Well, x phi, okay, we need to take the partials of all this stuff with respect to phi, so that gives you cosine phi, cosine theta, cosine phi, sine theta, and negative sine phi. Right? Now, what is x theta? Let's give myself a little room over here. X theta. Okay, well, I need to take the partials with respect to theta. So negative sine phi sine theta, sine phi cosine theta, and the theta partial of this is 0, of course. So I've got these. N is just the cross product. Let's say x phi cross x theta. Right? So take these two vectors, cross them. That gives your N. This is just F dot in d phi d theta, and that's a double integral that you can compute. Does that make sense? Yeah.
Just a question.
Yeah.
You have to do the cross product in that order. E theta.
No, well, let's see here. You have to do the cross product and then worry about whether you did it in the right order or not. Because it's the orientation business. So, good point. I really did kind of blow through that too fast. Once you do this cross product and find your capital N vector, it's not clear whether you've done it in the right order or not. So you have to look and make sure that your normal vector is pointing the direction it's supposed to. So in this case, because we're on H1, you need to make sure that your normal vector is pointing outward, which will be upward. In other words, the z component has to be positive. So make sure to check with that orientation. And that's true for all flux integrals that you brute force like this. Yeah. Is that cool? So this is part 1 of the problem. It's just a chapter 5 computation. And part 2 is to parameterize the lower hemisphere. It's going to be the same formula, it's just a different range of values of phi. Phi will go from pi over 2 to pi. Yeah. That'll give you the lower hemisphere. And then for the third part of the problem, you're going to do this disk, D, and that's parameterized. Well, that's actually easy to parameterize. That's just, you can parameterize it, from the XY plane, basically. It's a graph parameterization of Z equals 0. Yeah. And so though all 3 of these integrals, even though they're all very different looking integrals, what you're going to find is that because the vector field F, ZXY, because the divergence of this is 0, that means that this vector field is surface independent. And so all 3 of these surfaces, since they have the same boundary curve, all 3 of these surfaces will give you the same value of flux, even though they're totally different calculations. And that's kind of the moral of this story. This is a, kind of get your hands dirty and look and see how, oh my gosh, we got 3 same answers for 3 wildly different surfaces. And you get those same answers because this is a surface independent field. It's just kind of a see it up close and personal kind of exercise. Yeah?
Why shouldn't the flux in the disk be 0?
Let's see, off the top of my head, I'm not sure if it is. Let's see, maybe. Let's see, on the disk, let's see, Z is going to equal to 0.
Because it's a closed boundary.
Let me think now.
I wish I
So
know the flux is
Z
not a gradient.
to Y. Yeah, actually, I think it will be 0. I think all 3 of these will be 0. Now that you mention it, I mean, that's not really the point of the problem, but I think you're right. I think all 3 of these will be 0. Yep. And that's okay. I mean, there's nothing. That's not particularly. It's a good observation. Absolutely. That's not really the point of this problem, though. The point of the problem is that all 3 of these fluxes will be the same. Yeah, that's right. Yep.
All right, you've mentioned something. Maybe you can stop the recording because it's
Okay. Yeah. Is everybody okay with this problem?